Welcome back. We're ready to start chapter 21, which is called Electromagnetic Induction and Faraday's Law. In this chapter, we'll combine our knowledge of electricity and magnetism. All right, so we'll start off talking about an induced EMF. Remember, EMF is electromotive force, and it's basically the potential provided by a power source. So we're going to have an induced current, basically. We're going to have an EMF, a power source, that will drive a current. But we will induce it. We won't have a battery, or we won't be plugging into a wall. So that's the idea of induced EMF. And then we'll talk about Faraday's law of induction and Lenz's law. And that will definitely get us through the first video. All right, so let's introduce the chapter opening question. A coil of wire is attached directly to a galvanometer. There's a picture shown here on the right of the setup. There's a coil of water. This is a galvanometer that measures if there's current going through the wire. And there's nothing else. There's no power source. There's no battery here. Just the coil of wire attached to something that will register whether or not there's current going through that coil of wire. Back to the question. A magnet is inserted down into the coil. So we have a magnet, in this case being shown coming from above, and will be inserted down into the coil. It's left there for 1 minute, then it's pulled up and out from the coil. What would an observer watching the galvanometer see? So another way to ask that question is, how much current is flowing through the wire at any given time, if any? And there are a bunch of different possible answers. And we'll come back and go through the possible answers after we've gone through the chapter. But you can think about this. If you have a magnet being pushed down into a coil, will it induce a current? There's a magnet sitting there not moving, will it induce a current? If you remove a magnet from the coil, will that induce a current? All right, so let's talk first about induced EMF. This property of being able to induce a current was discovered by Faraday about 200 years ago. And he was looking for evidence that a magnetic field would induce an electric current, because he knew a current generated a magnetic field. He knew, for instance, if you have a current-bearing wire, then there's a magnetic field around that wire. So often in physics there's a correspondence. So if one effect will produce another, perhaps the other effect will produce the first. So he knew a moving current could generate a magnetic field. He wondered if a magnetic field could generate a moving current. And this is the basic idea of his setup. Here is an iron core ring, and on the left side is a battery with a switch, and if you turn on this switch, this coil will have current flowing through it. There'll be a magnetic field going through the inside of that coil. It's a solenoid, but since there's an iron core there, now it's an electromagnet. And not just that section of the iron core, but the entire iron circle here will be magnetized. So you're creating a magnetic field inside the coil on the right side, and he wanted to see if the presence of that magnetic field would drive charge and give us an induced EMF that would be measured on a galvanometer. That'll measure if there's current flowing in the wire. So what did he find? He found if he switched it on and just left it there, the galvanometer was at 0, just as it is when it's not switched on. But in the instant right when he hits the switch, just as the current is flowing through right initially and the magnetic field is just being fired up, so you're just having a magnetic field develop inside this coil, or at the moment when you open the switch and the magnetic field is decreasing through that coil. In those instances, while there's a change in magnetic field inside the coil, at that instance, then you have a current flowing through the wire. So that's what he discovered. He found no evidence when the current was steady or off, but he did see a current when the switch was turned on and off, while there is a changing magnetic field through the iron core, giving a changing magnetic field through the loop on the right-hand side. And so he determined that changing magnetic fields can induce an electric current. All right, that was one way to induce an electric current. Another way to have a changing magnetic field is just to physically bring a magnet towards or away from a loop of wire. So that's shown here. If you're bringing a magnet towards the loop of wire, will induce a current. If we're pulling the magnetic field away from the loop of wire, will induce a current. But the magnet is just sitting there, not moving, no current is induced. And one thing you'll notice is that when we're going towards the loop of wire, the current goes in one direction. As viewed from above, this would be clockwise. As you move the magnet away from the loop of wire, we induce a current again, but now the current is going counterclockwise. So the direction of the current does change, and we're going to have to be able to figure out that direction, but we'll get to that. All right, so we have a magnetic field induces a current, and so far we have two ways. One was Faraday's experiment, where he used a magnetic field that was changing because the current producing the magnetic field on the left side of that iron core, that current created a magnetic field through that iron ring, and that gave you a changing magnetic field in the loop of wire on the right side. Or the last slide, where we're physically moving a magnet towards or away from a loop of wire. The magnetic field then through the loop of wire is changing, and that induces an EMF, or a current, in the loop of wire. If we want to start talking about what's actually happening inside that loop of wire, we need to measure how much magnetic field is going through the loop, and that's what magnetic flux is. Magnetic flux is the amount of magnetic field going through the loop of wire. And what we'll see from Lenz's law is that the induced EMF is going to be proportional to how that magnetic flux changes through the loop. So we need to be able to define the magnetic flux, the amount of magnetic field going through the loop of wire, and it's given by this equation here. This capital phi, Greek letter phi, is sub b is our flux, and b is magnetic field. So that's our magnetic flux. That's our shorthand symbol for magnetic flux. That's equal to b perpendicular a. B perpendicular is the portion of the magnetic field perpendicular to the loop of wire, and geometrically you can figure that out as B cosine theta, so these are all equivalent. So let's go through the terms here. B is the strength of magnetic field, we measure that in Teslas. A is the cross-sectional area of the loop of wire. As shown here on the right, it's a square, so the area here would be length times length, or length squared. So there's A equals L squared. Alternatively, if it were a circle, and often we have a circular loop, the area of a circle is pi r squared. So that's a good equation to have for this section. And then theta is the angle between the direction of the magnetic field, shown here going from upper left to lower right, and a line perpendicular to the face of the loop. And that's so that this B cosine theta becomes this perpendicular component of the magnetic field. So you could do a little bit of trig and check. So be very careful with theta. Theta is not the angle between the plane of the wire and the magnetic field. It's the angle between a perpendicular to the plane of the wire and the magnetic field. All right, so we said to induce an EMF, we have to have a change in magnetic flux. So to change the magnetic flux, we have to change one of these three variables. We can change the strength of the magnetic field, and that's what we've done in our first two examples. Again, with Faraday's law, the changing magnetic field inside the iron coil, or with our second example, moving the magnet towards or away from the loop, we change the amount of magnetic field going through the loop of wire. We could also change the cross-sectional area of this loop of wire. We could deform the loop, or we could change theta. We could rotate this loop of wire so that the angle between the magnetic field and the plane of the loop of the wire changes. So we have three ways of changing the magnetic flux. We introduce a new unit for magnetic flux, and that is the Weber, WB. A Weber is just a Tesla times meter squared. So we'll sometimes see that unit up here, and that's our measure of magnetic flux. All right, so we said there are three ways we can change the magnetic flux. Here's our equation for magnetic flux here again on the bottom to remind us, and it's BA cosine theta. So we change any one of these three variables, and we change the flux. Shown in this example is what happens when we change theta, the angle between the direction of the magnetic field and the perpendicular to the plane of the wire, or the loop. So here's our loop of wire shown here as this three bands, and it's supposed to be an idea of, say, of a little spring, and we're looking at it edge on, and there's a magnetic field going from left to right. And so in this orientation on the far left, the magnetic field is going exactly parallel to the loop of wire. So absolutely no flux is going through the loop of wire. So our magnetic flux should be zero. No flux passes through the loop of wire, and that's indeed what we get out of the math. This is our loop of wire. We measure theta as the angle between the plane of the loop of wire and a perpendicular to that loop. So that's 90 degrees here. So theta in this example is 90 degrees. Cosine of 90 is 0, so the flux is 0. So the math agrees with what we should intuitively realize. If the magnetic field lines are parallel to the loop, no field lines are going through the loop of wire. All right, if we rotate the loop of wire a bit, as shown here, we're about 45 degrees now. Now we have some flux lines. Some of these magnetic field lines go through the loop of wire. So we start out horizontal, no flux lines go through the loop. We rotate a little bit, now the flux lines can go through the loop of wire, and we get a flux that is something greater than 0. So we'll have some value there. Cosine of 45 would be about 0.7. All right, if we continue to rotate so that our loop of wire is perpendicular to the magnetic field lines, what happens to theta? Theta is measured from the direction between the magnetic field lines and a line made perpendicular to the plane of the wire. So theta is now 0. So again, draw a perpendicular to the loop of wire and look at the angle between that and the magnetic field lines. That's 0. Cosine of 0 is 1, and the value of cosine goes between 0 and 1. So when you're at 1, you have the maximum value for cosine, and that gives us the maximum flux. So this orientation will give us the maximum value for our magnetic flux. This should make sense because now we have the most possible, in a given magnetic field, we have the most possible flux lines going through that loop of wire. When we start out horizontal and the field was going left to right, then no flux lines would pass through the loop. Go to 45 degrees, we have some flux lines going through the loop, and when we go perpendicular to the direction of the magnetic field, we get the maximum flux. So what we get from this slide overall is that the magnetic flux is proportional to the total number of field lines passing through the loop of wire. So we can define Faraday's law of induction now as the EMF, or potential, produced in a loop of wire is equal to the negative of the change in magnetic flux over time. Or if instead of having just a single loop of wire, if you have multiple loops of wire, then you just multiply by the number of loops. So if you had 5 loops of wire, you'd have 5 times the EMF. So we have a negative sign there. The minus sign gives the direction of that induced potential, that induced current. And the current produced by an induced EMF moves in a direction so that its magnetic field opposes the original change in flux. So what does that mean? Well, we know if we have an induced current in a loop of wire that the current will generate its own magnetic field. That was right-hand rule number 1. But we know now that we're changing the magnetic field. We have a magnetic flux to induce the current. So let's say you had the north end of a bar magnet approaching a loop of wire. We have a changing flux going through that loop of wire. The induced current will create a magnetic field that opposes whatever this change in flux is. So if I have the north end of the magnet approaching, then the magnetic field lines come out of the north end of the magnet. So I have an increasing strength of the magnetic field, in this case going to the right. To oppose the change in flux, I would have a magnetic field going back to the left. Since I have an increasing strength and field to the right, the induced magnetic field would be back to the left. So I do right-hand rule number 1 and figure out the direction of the induced current inside that loop to go back to the left. That would be counterclockwise. We'll go through plenty of examples. All right, let's give some visuals for this.
This is Lenz's law kit. It demonstrates very nicely how magnets behave when they fall down metal tubes. We have a slug of metal here, and we're going to drop it down the tube, and there's a nice window in the tube so you can see all the way down. Boom, down she goes. Turn it the other way up, and still it'll go down at good speed. It's called gravity. Well, now, if we were to make a magic pass, drop it down again, something else might happen. Look at that. Extraordinarily slowly. And the other way up. Oh my, oh my, oh my. Well, of course, it was a sleight of hand. This is highly magnetized, and this little buddy I showed at the beginning is not magnetized at all. The highly magnetized one is creating a little eddy current in the tube, which itself creates a little magnetic field that opposes the descending slug of metal. And it's trying to stop it going down. A nice demonstration of it, too. Lenz's law kit.
All right, so that's a nice demonstration of Lenz's law. So what was happening when you dropped the magnet down through the tube, he said it fairly quickly, was that the moving magnet created an eddy current. So what was happening? You had a magnet that was moving through that copper tube. The copper tube is a conductor. The moving magnet has a magnetic field with it that's changing because it's moving, changing through the conductor. So that generates a current, and then the current is set up in a direction that creates its own magnetic field, and that magnetic field opposes a changing magnetic field from the falling magnet, and so that opposing magnetic field slows it down. So that's a visual for what's happening. It's not something we tend to see in everyday life or experience, so that's a really nice visual showing Lenz's law in action. All right, let's give ourselves another example. And so here is a loop of wire again connected to a galvanometer, and we'll move a magnet towards the loop of wire or away from the loop of wire. Before I go into this any further, just to relate back to that video, instead of a loop of wire in the video, it was a copper tube, but it's all a conductor. So it was generating a current within the copper tube that was creating its own magnetic field that opposed the change in flux from the moving magnet. So here it's a bit simpler visually that we just have a loop of wire and we'll drive a current within the loop instead of within the entire copper tube. All right, so let's look at this. And I'll go through sort of the shorthand way to think through Lenz's law. So here we have a magnet, and it's oriented to the North Pole is upward, and it's approaching the loop of wire. So the magnet moves up towards this coil. So the magnetic field inside the coil is increasing because the magnetic field is stronger as we get closer to the magnet. So as we bring the magnet closer to the coil, we have an increasing magnetic field inside the loop. So the flux inside the loop is increasing. The magnetic field from the magnet is facing up. The magnetic field from the induced current is going to impose the change, so it will have to have a magnetic field that is downward. And to get a magnetic field downward, we can think of our loop of wire, figure out the direction of current, so you get a magnetic field downward. And when viewed from above, that would be, as shown in the diagram there, as viewed from above, that would be clockwise. In contrast, if we have the north-facing pole of the magnet upward, and we're pulling the magnet away from the loop of wire, now we have a decrease in the magnetic field through the loop of wire. So the flux is decreasing, and the magnetic field is still pointing upward. If we're going to oppose the change, if we have a less magnetic field going up through the loop of wire, to oppose that change we need more magnetic field going up through the loop of wire. So the induced current will have a magnetic field that goes up through the loop of wire. That would be a current, when viewed from above, that is going counterclockwise, as shown here. All right, that's the shorthand way to figure out the direction of the current, but there's a really nice set of steps that you can go through systematically given in the textbook. All right, before we do that, I'm going to give you another visual. All right, in this video, we get another demonstration of Lenz's law. We're again bringing a magnet towards a loop of wire, and it is generating a current within the loop of wire. And you can see the direction of the current switches. As the magnet approaches, the current in the wire, in the front of the wire, is going up. As the magnet approaches, right now, there goes a current upward, the red line. And then as the magnet is being pulled away, in the front of the loop of wire, this right-hand side of the loop of wire, it's going towards it's up. As it's pulling away, it's going downward. And you could compare, think about the magnetic field from the loop of wire. As it's approaching, it's going to the right. As it's pulling away, it's going to the left. And you can work it out and see that the generated current, whichever direction it's going, is creating a magnetic field, which is shown in purple, going in the opposite direction to the change in flux provided by the external magnet. So it's another visual for Lenz's law. All right, let's do a little review. So we can produce an EMF in three possible ways. They're given right in that equation for magnetic flux. It's BA cosine theta. We can either change B, the magnetic field, and we do that by, say, bringing a bar magnet towards or away from the loop of wire. We can do it by changing the A, area in the loop, and that's shown here. As an example, here's a magnetic field shown with the blue X's. So the magnetic field is going into the page or into your screen. And we have a nice round loop of wire here, and we're going to deform it. So it'd be like taking this loop of wire, and we're going to deform it by pulling it out, and we decrease the cross-sectional area inside the loop of wire. So we're changing the area of the wire, and that will create a change in flux, and the direction of the current is shown there. And the third way we can induce an EMF is to change the angle. The magnetic flux will change if the angle between the loop and the field changes. Again, that falls out of the equation. The flux equals BA cosine theta, or changing theta. So here, where the flux is perpendicular to the magnetic field, or theta equals 0, we get the maximum flux. And here, when we rotate it 90 degrees, there's absolutely no flux going through that loop of wire. The flux is going into the page, and the wire is oriented, so those flux lines are just going parallel to the plane of the loop of wire, no flux. All right, so that gives us our three ways we can induce an EMF. Change B, the magnetic field, change A, the cross-sectional area, or change theta, the angle between the loop and the magnetic field. To get the direction of that induced current, here are the three steps. The fourth is just an extra factoid. Here are the three steps to figure out the direction of the induced current. These seem to work quite reliably for students to go through these steps. What do we do? First, we determine whether the magnetic flux is increasing, decreasing, or unchanged. Then we apply this knowledge. The magnetic field due to the induced current will point in the opposite direction to the original field if the flux is increasing, in the same direction if it is decreasing, and is 0 if the flux is not changing. With that knowledge, then we apply the first right-hand rule, that we point our thumb in the direction of the current, fingers will point in the direction of the magnetic field, and that way we can determine the direction of the current that will give us the result we need from step 2. And then we're done. We know the direction of the current, that's what we're headed for. The fourth piece is just a factoid, and that says, remember the external field, the one that's changing, say, as you say, take a magnet, approach your loop of wire, and you have an increasing flux, or pull your loop away and you have a decreasing flux. That external field and the field due to the induced current, we're generating a current in this wire and it has its induced current. Those two fields are different, two sources of magnetic fields. All right, so let's go through those steps. Here's an example from the text. We have a magnetic field shown in blue here. The magnetic field is coming out of the page. That's what a circle with a dot in it means. It's like an arrow coming right at you. So there's a magnetic field going out of the page within this rectangular area. We have a loop of wire that is sitting within that magnetic field, and we're going to remove the loop. We're going to pull the loop to the right out of the magnetic field. So we start out with lots of flux lines going through that loop. We pull it to the right, and there'll be no flux lines going through the loop. So that's our setup. Now we'll go through our three steps. Determine whether the magnetic flux through the loop is increasing, decreasing, or unchanged. In this case, we start out with flux lines going through the loop of wire, and then as we pull it off to the right, there's less than no flux going through the loop, so the flux through the loop will be decreasing. Oh, and I always make note of the direction at this step also, because it just makes the next step easier. So the direction of the magnetic field, the external magnetic field, was out of the page. And to clarify, since we're removing the loop from the region of the magnetic field through the loop is decreasing. All right, next step. We apply the knowledge given in the second step. Magnetic field due to the induced current points in the same direction as decreasing. So I've just bolded the words we need for this example. We know the flux is decreasing, so the magnetic field due to the induced current will point in the same direction, so it will also be out of the page. And now our final step is to apply the third piece, which is right-hand rule number 3. So we need a magnetic field from the induced current, the current induced in that loop of wire, to be out of the page. To have a magnetic field from the induced current be out of the page, do right-hand rule number 1 and figure out whether we need a clockwise or counterclockwise current inside that loop. So here's the loop of wire. To get a magnetic field to come out of the page, come out through the loop, then my thumb will be pointing to the right at the bottom of the loop, and that is a counterclockwise direction. So our direction of the current within that loop will be counterclockwise. So to me, this is some ways it's harder because there are many steps. I sort of like the quick approach of just saying change in flux, figure out the direction of the induced current to oppose the change. But for learning it, I think breaking it down into these bite-sized pieces tends to help. So we just go through the 3 steps methodically and we get the direction of the induced current, which in this case would be counterclockwise. All right, let's try another one. In this case, we're going to have a loop of wire and we're going to shrink the size of the loop. A shrinking loop inside a magnetic field, and the direction of the magnetic field is again into the page. So again, here's our loop of wire. Imagine a magnetic field going into the page and we decrease the size of the loop. Do we induce a current, and if so, what's its direction? All right, so we'll go through our 3 steps again. Determine whether the magnetic flux is increasing, decreasing, or unchanged. So think about the number of flux lines that would be going through the loop of wire. You have a magnetic field going into the page, and you start out, and let's say there were, as shown there are 3 flux lines starting out, and we decrease the loop of wire. When we're done, there's only 1 flux line that's now going through the loop of wire. So visually we can see the magnetic flux through the loop is decreasing. Oh, and again, I make note of the direction. The magnetic field is going into the page. It points in because that makes my next step easier. So if it's decreasing, we again read through our second example, and this time I didn't highlight it, so you have to sort of find it. The magnetic field to the induced current points in the same direction if it is decreasing. So again, it's going to point in the same direction. So the magnetic field points in here, so the magnetic field to induced current also is going to point in. So now we use our first right-hand rule to determine the direction of the current. If we want to have a magnetic field that goes in through the loop of wire, take your fingers and go into the loop, and what's the direction your thumb giving you? It's giving you a direction that is clockwise. So we're done. Let's try another one. Here is our example now is a loop of wire, and we have the north pole of the magnet moving toward the loop into the page. So there's our geometry. I'll turn it around. There's our geometry of the plane of the page, and the north end of the pole is approaching the loop of wire, but this is how it's shown. So loop of wire, we see the south end of the magnet because the north end is facing away from us. It's approaching the loop of wire, moving into the page. So we go through our steps again, and I've actually made them a little bit more of a shorthand. So determine whether the flux is increasing, decreasing, or unchanged. If the magnet is approaching the loop of wire, then we're going to have an increasing flux through the loop of wire, so the flux is increasing. And again, I make note of the direction. The direction that magnetic field is into the page. It's the north end of the magnet. Magnetic field lines come out of the north end, so the direction of the magnetic field going through the loop of wire is into the loop, or if we rotate it here, it's into the page. All right, so our second step here, the magnetic field due to the induced current points in the opposite direction to the original field if the flux is increasing. So we know the direction of the magnetic field was into the page here. The magnetic field and induced current will be in the opposite direction, so it will be out of the page. Opposite direction, out of the page through the loop. Now we use our first right-hand rule. How do we get a magnetic field from an induced current coming out of the page? Use our right-hand rule number 1. Get my fingers coming out through the middle of the loop. Then at the bottom of the loop, my thumb points to the right, and that is a counterclockwise direction. So counterclockwise. How about one more? Here is a loop of wire. Here's our magnet, and the north magnetic pole is moving toward the loop in the plane of the page. So think that through. Do we have a change in flux? Our magnetic field lines come out of the magnet, and the magnet is approaching the loop of wire, but the loop of wire is parallel to those magnetic field lines. So there are no field lines. It's not like when it's arranged perpendicular, now we have a change in flux. There are no field lines going through that loop of wire. So if we go through our steps, determine whether the flux is increasing, decreasing, or unchanged. As it approaches from the side, there are no flux lines going through the loop, so it's unchanged. Direction of the magnetic field is to the right. I included that for completeness, but we don't actually need that information now because the magnetic field due to the induced current is 0 if the flux is not changing. So if we don't have any change in flux, we don't have any induced magnetic field, so we don't have any current to induce that magnetic field, so we have no current. This geometry will not induce a current in the loop of wire, or bring something in directly to the side. No magnetic field lines go through the loop of wire, no change in flux. All right, let's do one more. Here, when we rotate the loop of wire, we pull the left side towards us and pull the right side in. What's going to happen? All right, so we start out with a magnetic field going to the left, and we're rotating the loop of wire. So we're going to have a change in flux. We're changing that theta value. We start with no flux when we're in the same plane as the loop of wire, and as we rotate it, we are getting an increase in flux going through that loop of wire. So determine whether magnetic flux is increasing, decreasing, or unchanged. It's increasing. We go from originally 0, the magnetic field is parallel to the plane of the loop of wire. We rotate the loop of wire, we're increasing the flux. We have an increasing flux, so the magnetic field due to the induced current will point in the opposite direction as the flux is increasing. So if the magnetic field is to the left, the induced current is going to create a magnetic field to the right. So opposite direction or to the right. So to get the direction of the induced current, we apply the first right-hand rule. So here's our loop again. We're rotating it so that the left side comes towards us. We want the induced current to be to the right, so in that direction, back to the right. And so to do that, we get a direction of the current that is going counterclockwise. I only rotated the loop about an eighth of a turn in order to be able to see our direction more easily. If we'd gone to 90 degrees, then it's hard to tell which way is clockwise and counterclockwise because it's edge on. That's a good block of examples for Lenz's law. I changed things up from the book, and I will go through this one because this is a potential source of confusion. I flipped the magnet around from our third example before. So now instead of having the north magnetic pole approaching the loop, I have the south magnetic pole approaching the loop. And what's the difference is that magnetic field lines are coming back towards the south pole. So it changes the direction of the magnetic field through the loop of wire. As the south pole approaches the loop of wire, magnetic field lines are going back towards the south pole, returning to the south pole. So we determine whether the flux is increasing, decreasing, or unchanged. As the south pole approaches the loop of wire, we have an increase in flux. That didn't change. What's the direction of the magnetic field, though? The direction of the magnetic field as the south end approaches is going to be out of the page because the magnetic field goes towards the south pole. So that changes from our previous example of the north pole approaching the loop. So the magnetic field is increasing, the flux is increasing inside the loop. The magnetic field due to the induced current will point in the opposite direction if the flux is increasing. So the magnetic field due to the induced current has to be into the page. So opposite direction, into the page. Now we use the first right-hand rule again to determine the direction of the current. To have a magnetic field going into the page, the current has to be clockwise. That's a good block of examples. Let's go back to our chapter opening question. A coil of wire is attached directly to a galvanometer. A magnet is inserted down to the coil, it's left there for 1 minute, then it's pulled up out from the coil. What would an observer watching the galvanometer see? Option A, no change, because there's no battery, there'd be no current. We now know that's not the case. We know if we have a changing flux inside the coil, we can induce a current. So when the magnet is approaching the coil or being pulled away from the coil, then we have a change in flux and will induce a current and something will show up on the galvanometer needle. So A is wrong. What about B? A small current flows while the magnet is inside the coil of wire. Well, when it's sitting there not moving, there's going to be no current. There's no change in flux, so no induced EMF, no current. So that's not a very good answer. How about C? A current spike as the magnet enters the coil and then nothing. Well, that gets us partway through. As the magnet is being inserted into the coil, we do get a spike in current. When the magnet's just sitting there not moving, we won't see anything. The galvanometer will be at 0. But we have a third step here. Then it is pulled out from the coil, and that will induce an EMF as well. So that's not a full correct answer. Let's see, a current spike as the magnet enters the coil, and then a steady small current. That's absolutely wrong. Well, there is a current spike as the magnet enters the coil, but there's no current while it's just sitting in there. While it's sitting in there not moving, then there is no current. So that's not right. And here, the longest answer, often a hint that that might be the correct answer, although I try not to do that in exams, but this is our only remaining possibility, so hopefully it's right. A current spike as the magnet enters the coil, and that's correct. As the magnet's entering the coil, we have a changing magnetic flux, we induce a current. Then nothing, and that's true. While the magnet is sitting in there not moving, we won't get any current. The galvanometer will be at zero, pointer at zero. Then a current spike in the opposite direction as the magnet exits the coil, and that's correct. As we remove the magnet from the coil, then we get a current in the opposite direction as we had when it was entering the coil. So that's our best answer. All right, that finishes chapter 21, a nice introduction to induced EMF and conceptual applications of Lenz's law. And I recommend you practice some of those a bit and then come back and we'll work on the next sections for chapter 21. See you then.